I've got some trivial question. What would be the acoustic counterpart of your microwave experiment?
Microwave experiment?
Yeah. How could you turn this into an acoustic absorber? You could use the exact same configuration?
Oh, no. It's quite different, in fact. Although the final result, when you see the absorption spectrum, looks similar, but the underlying physics is quite different. Yeah. Thank you for asking.
But Professor Sheng, in fact, if you have acoustic pressure waves, it's almost as if you would have only one electromagnetic wave polarization, isn't it? TE, for instance.
It's more than that, because the electromagnetic wave is the transverse wave, and the acoustic is the longitudinal, and the transverse wave is very rich, but it's also more complicated, than the acoustics. So I don't know how to answer your question adequately.
Okay.
I'm sorry.
Yeah, no problem. So would there be any more questions, please, people in the audience? I'm sure you have many questions. I mean it.
Do you see me, Sebastian?
Yeah, sure. Martin, please come forward.
So thank you very much for the nice talk. It's amazing how far one gets with intuitive ideas for designs. But my question is the following. Here you have a very clear target. You have emphasized it at the end, the relative bandwidth and the relative thickness. So would it not be a good case for a numerical optimization procedure, such as, for example, topology optimization, to really optimize these kind of structures further?
To answer your question, this is a very good question. In fact, what I present to you is really a simplified final picture. To arriving at this picture, we have already done quite a bit of optimization in terms of the dimensions. Otherwise, the performance cannot be so good. So the framework or the underlying physics idea, for example, the magnetic resonances, these can probably be predicted, but their precise frequency and things like that cannot be predicted. So that really needs to have simulation and also optimization. But if you mean to put in, artificial intelligence, also something like that to further optimize, we have not tried that. I don't know. But as far as I know, if we use artificial intelligence, things like that, it needs a lot of training. So we need to have a large number of cases, successful case or not unsuccessful case, to train these softwares. Then they can produce marvelous effect, maybe. Otherwise, they cannot produce some structure from nothing.
Yes, I perfectly agree. Actually, I would not think that this is a good case for machine learning, because here you want the answer to one question. For machine learning is rather good if you want the answer to many different questions. That's why I was asking about topology optimization, which perhaps goes beyond what you have done, because when you say you have done optimization, you do it under certain constraints, that your cross mesh, for example, is the starting point. Perhaps you might get even better results if you give up these constraints.
That's certainly can be true. Yeah. I do agree with you. Yes. Yeah, that's certainly true. Yeah. But I think we just set out a framework, and I think it would be good if people can follow this up by using different topological considerations. Indeed. Yeah.
Thank you very much.
Thank you.
So people, please come forward with your question. I just had another very trivial question. So you mentioned a few times the checkerboard configuration. So you think this very configuration of the checkerboard as something essential to do with the fact that it would be almost optimum for the absorption?
No, the checkerboard is really set up to make the absorption polarization independent, essentially.
Okay, okay.
Yeah.
Okay, because there are some very interesting, theorems like Keller's theorem and so on, and, duality theorems on the checkerboard and so on. And I don't know.
Oh, I see. Oh,
it's related
okay.
to effective properties and perhaps, yeah.
Yeah.
Okay.
Yeah.
Anansa Ramakrishna, so Professor Anansa Ramakrishna from Indian Institute of Technology, Kanpur, looked at extraordinary transmission through checkerboard-like structures. He calls this plasmonic checkerboards, and I find this very interesting because it's the total of opposite of what you try to achieve.
I see. Aha. Okay.
And this was really linked to the checkerboard
geometry. Yeah. Okay.
Yeah.
Okay.
So, any more questions, people? It's a unique opportunity to ask your questions to Professor Sheng. It's a great opportunity.
Sebastian, can I ask a question?
Yeah. Please come forward, Mohamed.
Yes, thank you. So you presented this absorber for the gigahertz and the 5G, but now people are researching on the 6G that will be working on in the terahertz domain. So can your concept be extended to the terahertz regime by using the same ideas?
That I cannot really comment to, because each frequency regime may have a different optimal geometry for absorbing things like that. So I cannot comment on that. But usually higher frequencies are easier to absorb. That's the usual rule. But of course, so we know terahertz can be somewhat dangerous because they they are close to the human cells biological, it can destroy biological structure. It can detect biological signatures. So it's a little bit it's a little bit different. I have to say maybe there are optimal ways, better optimal ways for terahertz. We are only thinking right now in a microwave regime, not yet to the terahertz.
Okay, thank you.
Yeah.
Do we have any more questions in the audience? Ooh. Okay, I've got another question which might look a little bit crazy, but could you turn your experiments in something which would be three-dimensional? Could you turn your structure into something which would be, well, really three-dimensional, with triple periodicity? So in all three directions.
Well, with diffraction and the hierarchical structure, we are already partially 3D, okay? Not completely 3D, but partially 3D. You want to make a completely 3D, but we need to have a target goal, what we want to achieve with such a structure. Then we can probably think more rationally about the structure that can achieve the goal.
But your approach, do you think your approach is a good one to add this third dimension? I mean, to use the exact same kind of, algorithm? Or would it break down if you now have, elements in the third direction?
Yeah, you definitely can. For example, you can extend this to a lower frequency range. But the whole sample, of course, will be much thicker. Definitely, yes. You can have a 3-layer self-similar structure, yes. So the answer to that is definitely yes.
Okay, thank you. So do we have any more questions? And this could be like me very, trivial questions or more advanced one. And not necessarily on microwaves, because Professor Sheng is very famous also for elasticity and acoustic devices. I think actually what you have done might be translated into something, like absorption of elastic waves in plates. I mean, maybe there are ways to, translate your approach to acoustics or elastic waves with similar reasoning.
Okay, you are the expert.
No, but usually people they try to use electrical circuits and then they make up stuff with acoustics and there's something here which obviously your two parameters now they would be like the compressibility and the bulk modulus, for instance, instead of permeability, but maybe something similar. Okay, so if we have no more questions, I would like us to thank again Professor Ping-Shen for this wonderful talk on a topical topic subject, and yeah. Bravo.
Okay. Thank you.
So thank you, Professor Sheng, and
thank you very much.
Stay safe. And Bogdan, who is our seminar speaker next week? Please help me.
I'm sorry, my microphone was off. Yeah, next week we will have Ying Wu from
Post King
Saudi
Abdullah
Arabia.
University. Yeah, fantastic. So King is heading a group in computer science and applied physics, and she works a lot on topological crystals and these kinds of stuff. Okay, thank you very much, people, and please stay safe and take your vaccine like I did recently, so I'm not really feeling so well.
Hope everybody gets vaccinated soon.
Yes, we need to. Rough time. Bye-bye.
Bye.
Thank you, everyone.
Thank
Bye.
you.